Welcome back. This is Unit 1, Section 7, Inverse Functions. This is video 2. We're going to jump right in. So we're talking about finding the domain and range of inverse functions. That's where we're going to open up here. So we're going to have two circles to try and understand this. So we have the domain of f, and here we have the range of f. So if f takes A to B, and what this means is that if I take f of x and I input A, it'll equal B. If you ever see any arrows like this with function notation above them, that's what it means. I can take A from my domain and it will give me B in my range. So now for my inverse function, this becomes my domain and this becomes my range. And it will take B and plot it back to A. So something we can do is we can restrict domains to create inverse functions. So I guess, for example, if we had f of x equals the square root of x, then you could say that f of -1 of x equals x, or f inverse of x equals x squared. Because it undoes the square, right? So they're inverses of each other. But only from 0 to infinity. And that's because of this guy. There cannot be more than one inverse. So that's also something to keep in mind. Once again, the range of f of x is the domain of the inverse, and the domain of f of x is the range of the inverse. Just like what we were talking about. Okay. So we are going to identify which of the toolkit functions, that's all of these functions, besides the quadratic function, are not one-to-one. So we already know this is not one-to-one because it tells us. So what one-to-one means is that if I have a value of x and I put it into f of x, I can only have one y value for every a value. So I can't have, I guess if we did it like this. It can be like this. It has to associate with only one. So if we had this, or I'm sorry, not that, this, where x1 went to y2 also, then that is not okay. So another way of looking at this is the horizontal line test. That tells us what is one-to-one. Remember that one? So that says it can only touch a maximum of one time before it will cease to be one-to-one. So like this function, that's the quadratic function. I can draw a line And since it intersects twice, it is not 1 to 1. So let's identify some of these. So the constant function, we'll do that one here. That is a function that looks like this. Is that going to pass the horizontal line test? No, because it's a horizontal line. Literally every point on the line will touch a horizontal line. So it is not 1 to 1. There really is no domain that we could restrict it to be 1 to 1. It wouldn't really mean anything anyways. It would just be a point in space. Okay. So our identity function. Let's get another piece of paper. This is f of x equals x. So notice it passes the horizontal line test, so it is 1 to 1. So therefore, it does have an inverse. And it will have an inverse for every value. All numbers, it'll have an inverse. Now let's have a look at a cubic function. Notice that no matter where I place my horizontal line, it's 1 to 1. So it will have an inverse over its entire domain. Now here, we are going to have the reciprocal. That will be this guy. So this one, it's 1 to 1. It would have an inverse. Over the entire domain. Now, let's get a new page. There we go. Now let's take the reciprocal squared, the square reciprocal. Remember this one? Now, no matter what I do, I will get 2 points. So while this one is not 1 to 1 on its entire domain, it is 1 to 1, not including 0, remember, because we can't include 0, all the way to infinity. So it is 1 to 1 from 0 to infinity. This is not 1 to 1, and this is 1 to 1. So now let's have a look at a cube root. That's a cube root. This one is 1 to 1. Now, let's get, I think I have one more new page. Oh, I don't. All right, well, let's put it in here. So if we have, we'll compare this to the square root function. This is 1 to 1. So what about the absolute value function? We just had a look at that one. Well, it looks like it's not going to pass. So it is not 1-to-1 normally. But if you restrict the domain to 0, because it can take on the value of 0 to infinity, then you will get a 1-to-1 function. So you would get this half. Okay, finding and evaluating inverse functions. So a function f of t is given by this table. Now we're going to find and interpret f of -1 of 70. All right. Remember, it takes an output of the original function. So it's going to take one of these numbers, and it's going to give us one of these. So if I take 70, then that would equal 90. And that's how you read it from a table. Pretty simple. What this says is that, so if f of 90 equals 70, so if in 90 minutes I can drive 70 miles, then what this one says that it takes 90 minutes to, it takes, it's got to be backwards. Okay. It takes 70 miles to drive 90 minutes. So if I wanted to be in the car for 90 minutes, I would drive 70 miles. Why on earth? I guess you would need to compute it like that. I'm trying to think if I've ever done that in my adult life. Actually, yes. If you go on very long road trips, you will usually break up the trip by driving time first, not driving distance. So you would say, oh, I only want to be in the car for an hour and a half. And then you would figure out how far you can make it in an hour and a half. Now, evaluating the inverse of a function given a graph of the original function. So you saw earlier in, I think it was unit 1 or 2, that the domain of a function can be read by observing the horizontal extent of its graph. You find the domain of the inverse by observing the vertical extent of the graph of the original function. So if this is my original function, and it's 1-to-1, so it'll have an inverse. Instead of going along the x-axis to find my domain of my original function, I'm going to go along the vertical axis, right here. And that's the domain of f of -1. Now, if we wanted to find the range of the inverse, we would have to look at the domain of the original function. So let's look at an example. So this function g of x, we need to find g of 3 and we need to find g of -1, 3. So the first thing that we can do, so to find g of 3, remember this is where x is equal to 3. We're going to go to x equal to 3. And what is our function value? Looks like it's 1. So now our point is 3, 1. That's what that point is on our original function. So now, this is the tricky one. The inverse of g at 3. So remember, this is now an output value. So this is going to be a y. And we're going to find what corresponding x that we need. So let me see. Our y is 3. You go all the way across, all the way down. So we're going to have 5. So what that tells us is we will have a 0.53 on our original. So remember, if you needed to find the value of an inverse function from the graph of the original, what is on the inside is now a y value. So you use that y value to find your x value. Inverting the Fahrenheit to Celsius function. So this, we're going to get into like the beginnings of finding inverse functions. So this is a formula. So we have c of f. What we want is f of c. So therefore, let me erase that. So therefore, I am going to solve for f. I'm going to multiply by 9 over 5. So we have 9 over 5c plus 32 equals f. So this is the conversion from Fahrenheit to Celsius. So it undoes. So it undoes the Celsius calculation. So you can think of it as an inverse. Now we're going to find the inverse of this lovely function. So the first thing that we're going to do is we're going to put it in y equals form. Since it says find the inverse of the function, I'm assumed it was 1-to-1, but you will need to check that it is 1-to-1. This one is. So don't worry about it. 1 over x is 1-to-1. So now what we're going to do is we are going to solve for x. So we're going to have y minus 4, and that's because we subtracted this 4 from both sides. Now this is the tricky one. So I need this x minus 3. I need my x by itself. So I am going to multiply both sides by x minus 3. But I am not going to FOIL. I'm going to leave it like this because it'll be easier to determine what I need to do. Now I need to divide out y minus 4. So that I get x minus 3 equals 2 over y minus 4. Now I need to add 3 to both sides. Okay. So there's 2 ways we can do this. You can say f inverse of y equals 2 over y minus 4 plus 3. Or you can say f inverse x equals 2 over x minus 4 plus 3. You can actually make this a y, and you can actually make this an x at the very end. And they're equivalent. These are the same thing, just different variable. With the y inside, it may be easier for some people to understand that it's actually taking an output value and giving you an input value. Okay, so solving to find an inverse with radicals. Okay, so what is the first thing we are going to do? We're going to make it y equals. And then what are we going to do? Well, I would suggest getting the square root alone. So I'm going to have y minus 2 equals the square root of x minus 4. Now I'm going to square it. And now I'm going to solve for x. X equals y minus 2 squared. And then if we move this 4 over, make it a plus 4, we get plus 4. So if you were to carry it out in exactly the same fashion here, you would get this. Y minus 2 squared plus 4 equals x. You can see that these are equivalent. I just switched it around, and we're allowed to do that. So therefore, our inverse or like this. Now, domain, since it's a square root function, we do have to take that into consideration. So we need x minus 4 to be greater than or equal to 0. So x has to be greater than or equal to 4, which means that 4 infinity is the domain of our original. Now, what's the range of our original? So, output values of y for a square root function so if we had just a square root function, our output values of y would never be less than what was I going to say? They can never be less than 0. That's right. I'm sorry, I completely forgot. So yes, radicals can never be less than 0. So if you have the radical of x, the square root of x minus 4, so what you're doing when you subtract that 4 from the x on the inside, you're actually only shifting it like horizontally. So it won't change any of the y values. So this is equivalent to saying you could add the 2 at the end. That's okay too. So I'm going to go with that form. So in terms of the range of this function, we're shifting it up 2. So it would cut off at 2. So it would give us anything 2 or greater than 2 for our range. And this is our original. Now, for our inverse, our domain is now the range. And the range is now the domain is now the range. So let me see. For infinity. Finding inverse functions and their graphs. So one way you can think about the inverse function, let's get a little function up here. Let's say it looks like this. So this is x squared on 0 to infinity. and that's 1 to 1. So we can find an inverse of that. So first of all, it passed the horizontal line test. So it's 1 to 1, we're good. So that means it has an inverse on the restricted domain. Now notice this line y equals x. This is a line where you will be able to reflect across to find an inverse. So for example, this inverse looks like this. What does that look like? Well, that looks like square root function. All right. So now we're going to go into how to even get started on one of these. So we're going to sketch the graph of f of x. So I'm going to create this purple line. And I'm going to make the line y equals x. And that's just the line straight, diagonally straight through across. Y equals x. So now what are we going to do? Will we have an inverse, first of all? Because we need to check that. Is it 1 to 1? Which means, did it pass the horizontal line test? Well, it looks like it did pass the horizontal line test, so it is 1 to 1, so it will have an inverse. So now what? So it looks like the domain, it looks like, so all of the x values that this is going to be able to take, this is for our original, the domain is 0 to infinity. I don't think we're going to include 0. It looks like that's going to just shoot off, but not really ever touch 0. The range is equal to all of my y values. So that looks like positive infinity to negative infinity. So the whole lot, R, is what we would call that, all real numbers. So now I know that my inverse will have a domain of all real numbers, negative infinity to infinity, because that's my range of my original, which is my domain of my inverse, and then my domain of my original is my range of my inverse. Okay. So remember, another thing we do for inverses is we flip-flop x and y. So if we have our original, then we have our inverse. If we have 7, 1 on our original, then we'll have 1, 7 on our inverse. If we have 3, 4 on our original, then we'll have 4, 3 on our inverse. Works for negatives. If we have negative 3, negative 4, then we'll have negative 4, negative 3. So let me get to picking out some points here. Ones I notice immediately are this one and this one. So our original function has 1, 0 and 2, 1. So our inverse will have 0, 1 and 1, 2. Let me plot those points first. So 0, 1 and 1, 2. And what else do we have? So if I could do this. So if we have about, because this is an estimate, remember it doesn't go to 0, but if we have about 0, 3, right? Like right here, it does not cross, but it is about 0, 3. Then we will have about 3, 0. Is that? Oh, negative 3. Then we'll have about negative 3, 0. So it's about right there. Not quite 0. Now what else? Well, it looks like here I can estimate that it's going to be, this one goes to negative 3, 0. I can estimate it'll be about 4, 2. So my inverse should be about 2, 4. So 1, 2, all the way up to 4. And it looks like I can just graph this line now. And notice that's a reflection across this line. Be f of negative 1 of x. And that sums it up for inverses of functions. That actually sums it up for all of Unit 1. So congratulations for making it all the way to the end. I really appreciate you watching these. Thank you so much. Have a good night or day, and I will see you for Unit 2.